Hello chemistry students, and we're doing lesson 9.2 today, where we're going to teach you how to do mass-to-mass stoichiometry problems. And basically there's only one objective for this lesson, and it's written down below. Given the mass of a component in the chemical reaction, use stoichiometry to determine the mass of another reaction component. So this is part of the power and use of stoichiometry. Once you know the mass of one thing that's completely used up in the reaction, if it's a reactant, or the mass of product that you collect, you can then use the balanced chemical equation in our knowledge of moles to figure out the mass of any other component. So let's get to it. Actually, we'll start with just reviewing the overall strategy. You have to begin, as in all stoichiometry, with the balanced chemical equation, so that you know what the relationships are between the reactants and products.
And then you have to plan a strategy to go from the given amount to the desired ending amount. And to use that, we use this mole island down here that we have posted in the room.
So then it ends up being a dimensional analysis problem. So the kind of problem we're going to focus on today, you're going to get a mass of some substance, whether it's a reactant or product. And you can see the strategy. Take the mass, change it to moles of the given substance. Then we're going to go from moles of the given to the moles of the substance we want to. That's the mole-to-mole conversion that we just practiced. And then if we want the output to be in grams, we just take the moles of the desired substance and change it with the molar mass to the grams. So that's the basic approach to all of these problems. On to an example.
Alright, so the first one is 13.4 grams of hydrogen peroxide decomposes. We want to know what the mass of oxygen gas is produced. So first we have to set this up. It's H2O2.
And it's decomposition, so that's the only reactant.
And it goes to O2 and H2. And it's great that it's already balanced.
It is already balanced. Are all ones. Okay. So we have the starting point of 13.4 grams of hydrogen peroxide, and we want to end up with mass of oxygen. So how many grams oxygen equals 13.4 grams of H2O2. So now we're the first order of business. We want to go from the given mass to the moles. That's going to be a molar mass conversion, right?
Yep.
So what's our molar mass?
34. Roughly. I'm going off of my memory here.
34 grams, roughly, is 1 mole of H2O2. All right. That cancels out the gram unit. So now we need a mole ratio, which in this case is 1 to 1.
Yep, we know for every 1 mole of H2O2, we have 1 mole of O2 being produced.
H2O2, 1 mole O2. And lastly, we want to move from moles of oxygen to grams of oxygen. So we know that oxygen's diatomic. So it's going to be 32 grams.
And you hit enter on this, and it turns out to be, with significant figures, 12.6 grams of oxygen.
So if you decomposed that given mass of hydrogen peroxide, 13.4 grams, we could expect 12.6 grams of oxygen to come out the other side of the process.
Let's look at another problem.
Okay, so here's a metal reacting with hydrochloric acid. Typical result is always the salt of the metal and hydrogen gas. So we are given an amount of 6 grams of hydrogen gas, and we're asked how much magnesium would you have to react to come out with 6 grams of hydrogen. So how many grams magnesium equals 6.0 grams of hydrogen? So again, same approach. We want to go from grams of hydrogen to moles. That's our starting point. So 1 mole H2 is about 2 grams, right?
Yeah, 2.02.
2.02 grams. And And then we're going to use our mole ratios from our equation. And again, for this one, it ends up, the equation's already balanced here. That's 1, so it's still a 1-to-1 mole ratio. So 1 mole H2 is going to come from 1 mole of magnesium. So they are equimolar, we say. Alright, and then a mole of magnesium has the molar mass of
24.3.
Thank you, 24.3 grams right off the periodic table. And our moles of magnesium, all of our units have divided out except grams of magnesium.
Now we are left with 72, with the correct sig figs, grams of magnesium.
So if you completely reacted 72 grams of magnesium in as much hydrochloric acid as it needed, that would be what you'd need to get 6 grams of hydrogen gas.
All right, another practice problem.
So now we've got a combustion reaction here. The complete combustion of hexane is going to give us 12.6 grams of water. And the question is asking how much hexane was consumed and how much oxygen was consumed. Okay, so what we know is our starting point is 12.6 grams of water. We'll fence post this one, Mr. Hunter. Okay. So let's do, we need to do hexane and oxygen. Let's do the hexane first. So, but we're going to begin with the molar mass of water, which I believe is 18.02 grams. That's a 2 to 1 mole water. Alright, now this one's not a 1. Check it out, equation. 7 is the coefficient for water, 1 for hexane. So that means 7 moles water goes down here. And we get 1 mole of C6H12 to produce those 7 moles. So we've canceled moles of water, canceled grams. Now we just need the molar mass of hexane. A mole of C6H12 has a certain mass, and I bet Mr. Hunter has it worked out. 86.2 grams of C6H14. And I started writing 12s, and it's a 14. My bad. Okay. Did we do, that's the correct mass for the C6H14? Okay, so it was just my mistake, and it's C6H14.
Yeah, it comes out with correct sig figs to be 8.62.
So if you combust 8.62 grams of C6H14, you could expect to get 12.6 grams of water as a product. Now we're supposed to do the oxygen one. So the setup's going to be, we're going to start from our given, 12.6 grams of water. The beginning part looks exactly alike, 18.02 grams to 1 mole of water. But now the mole ratio is a little different here. 7 moles water equates to 9.5 moles of O2. And like Mr. Hunter said in the last video, it's okay on the diatomic ones to use halves, although we tell you not to. You will see it that way.
Technically proper, but it is.
But it works. It gets you to the same place. It's the same ratio. 1 mole of O2
equals 32 grams.
32 grams O2. And everything cancels except for grams of O2. And what do we get, Mr. Hunter? 30.4 grams of O2. So you can see this is a pretty powerful tool in predicting, inputs or outputs to some chemical process from one of the givens. So in conclusion then, I know the title of the video was mass to mass stoichiometry, but realistically we're going to start encountering, as we work through some of these problems in class, some of what we would call mixed stoichiometry calculations. And mixed means that the amount you're given and possibly the amount you're asked to calculate could be really any measurable quantity. It could be mass, could be moles, it could be the volume of a gas at STP, or it could be particles. So we need to be prepared to deal with that. In other words, to deal with the entire mole map. And that's what I've given you in this next problem. Mr. Hunter was unable to be with me, but let's take a look at this problem here, and then we'll see how we're going to use stoichiometry to get through it. So we have 3.7 moles of methane being combusted. So there's methane plus oxygen in a combustion reaction. We get, of course, carbon dioxide and water as products. We're given two tasks. First, calculate the STP volume of carbon dioxide, so the volume of this. Next, calculate the number of oxygen molecules required for the reaction. So we need to calculate the amount of oxygen in molecules, though, not in moles or mass. So it's really the same approach that we've been using. Okay, let's tackle the carbon dioxide one. We are given an amount of methane in moles, and we're asked to give the output in volume of the gas. So we're going to go from moles of methane to moles of carbon dioxide, and then we're going to take that to the volume of carbon dioxide. And so it's just tacking on a different kind of mole conversion at the end. All right, let's get this set up and work it out. So I've went ahead and set up this problem. I started with the given amount of 3.7 moles of methane. I then wanted to move from moles of methane to moles of carbon dioxide, so I set up a mole ratio here. Moles of methane are on the bottom, moles of carbon dioxide on the top. This one just so happens to be 1 to 1, so it's not mathematically going to change anything. So anyway, got a phone call, sorry about that. I started with the given, 3.7 moles of methane, put in the conversion factor to move from moles of methane to moles of carbon dioxide, and I know it's a 1 to 1, so mathematically it's not going to do anything, but it's going to change our unit. And then we're going to get rid of the moles of CO2 by this conversion factor that equates 1 mole of a gas, carbon dioxide's a gas, to 22.4 liters when we're at standard temperature and pressure. So our units cancel. Moles of CO2 cancels. We're left with liters of carbon dioxide. And then it's just a matter of taking the 3.7 times the 22.4 to come up with the answer. And this one works out to 83 liters of CO2. That would be the amount of carbon dioxide produced if we combusted 3.7 moles of methane. So here's the setup for the second question, which is to calculate the amount of oxygen molecules required, the number of oxygen molecules required. So again, starting from the given amount, we first put in a mole ratio, 1 mole CH4 to 2 moles of oxygen. Again, 1 mole CH4 up here, 2 moles of oxygen. That converts our unit to moles of oxygen. And then we just use the Avogadro's number equivalence, that a mole of anything is that many molecules or particles of it. Units are going to cancel out. The moles of methane divides out, the moles of oxygen divides out, and your unit comes out molecules of oxygen. And now it's just cleaning up the math. 3.7 times 2 times 6.02 times 10 to the 23rd. I just did the calculation. It worked out to 4.5 times 10 to the 24th molecules of O2 with the correct significant figures. So you can see, even if you're not going mass to mass, it's still mole conversions of some kind, whether it's volume to moles or moles to particles, which are things that we've already worked on. And the only new thing, again, is that we've introduced this idea of the mole ratio, which is going to come from these coefficients in the equation that lets you change from moles of one substance to moles of another. So we will definitely be practicing this a lot more in class. Until then, have a good evening. Alright, so now for some post-video questions. Magnesium reacts with hydrogen chloride, that's hydrochloric acid according to the equation shown below. We want you to predict the mass of hydrogen gas produced from a starting amount of 10.7 grams of magnesium. So we are saying you have 10.7 grams of magnesium. How much in grams of hydrogen is produced? Follow-up question then. Instead of asking for the output of hydrogen in grams, we could always ask you for the output in volume. How many liters of hydrogen is going to be produced in that reaction? And of course, we're assuming that standard temperature and pressure conditions for the gas. Give those a try, and we'll see how you do next time in class and work through some additional examples.